Hello and welcome to the beginning of our work on rational expressions. These are sometimes so large they're called the beasts. And you're like, oh my word, they are as ugly as can be. Why are they so ugly? Well, rational, remember this word ratio, the rational numbers were fractions. So let's put this up here. Fractions, that's what we're dealing with, but these are rational expressions, not just rational numbers, not just fractions with numbers in them. Now that we've done polynomials, we might stick polynomials in the fractions. Yeah, so it might look a little bit hard. So it is a really good thing to review a couple of things that we have touched on earlier. And there are two quotes that we did. This one was clear back in chapter 1 when we talked about simplifying stuff. And this one was back in chapter 2 when we were talking about word problems. So this one, I'm going to let Elder Scott read this to you himself. And when he's done, let's talk about it a little bit.
As you seek spiritual knowledge, carefully search for principles. Separate them from the detail used to explain them. Principles are concentrated truth packaged for application to a variety of circumstance. A true principle makes decisions clear even under the most confusing and compelling circumstances. It is worth great effort to organize the truth we gather to simple statements of principle.
Oh, isn't that nice to hear him say it? Right now, we note that principles are concentrated truth and they can be applied to a wide variety of circumstances. This is exactly what makes math so powerful. There were a few principles that you learned clear back in arithmetic, way back with fractions, that are going to hold true now. It's not something new, it's the same principle being applied to a very different circumstance, and that is when we have fractions that are made up of other things than just numbers, but the exact same principles will hold true. Even in these most confusing and compelling circumstances, those fundamental and basic principles are going to hold true, as we'll show you. So here we have the second one. Notice that we are going to be working with simplifying stuff. And this is important to be able to take something that's complex, confusing, and compelling and simplify it so that a child can understand what we're doing. That is our goal. John Taylor's quote is, "It is true intelligence for a man to take a subject that is mysterious and great in itself and to unfold and simplify it so that a child can understand it." And that's what we're going to do. This is going to be doing some abstract thinking, so not all children will be able to do this, but hopefully by the time we're done, you'll be able to see how fractions and what we did with fractions apply to rational expressions and be able to have them unfolded and simplified for you as well. All right, let's work on it. We start off with the simplifying of fractions. So if we were to take something like 6/8, and now let's simplify that, and you're like, oh, I can do that. That's you divide by 2, you divide by 2, you get 3/4. Well, let's do this in slow motion. You're exactly correct. 6 and 8, and you divide by 2 divided by 2. So you actually saw that this was 2 times 3 and 2 times 4. And then you said, oh, 2 and 2, that cancels. It actually, if you remember, that divides to 1 and then makes 3/4 there. So that divides off to 1. You factored this in your head. The same thing will happen with any number. What if we had something like 3x over 4x? We don't even know what's going on with the x's, but we do know that x's will cancel and simplify to 3/4. Well, let's try something else. How about x squared plus 5x over 3xy plus 15y. What if we did something like that? You're like, ooh, we could cancel. Look, there's a 5 and a 15. Okay, stop. We need to talk about something right now before we get into anything. You will notice that if we were to try to take 6/8 and say, hey, look at this. This is 1 plus 5 over 3 plus 5, and try to cancel these 5s out, we get left with 1/3. We need to be very clear on this because many of you will try to do that. You'll try to cancel numbers where there's a plus sign in here. Canceling is we divided that undid these multiplication symbols. You can't undo plus with divide. Divide doesn't undo plus. So these things, when things are added together, nothing is able to cancel until you do it in multiplication. And then you can cancel out 2's, or you can cancel out x's or anything. So crucial in what we're going to do is factoring. You've got to factor. This puts things in multiplication, which can then be undone with division. So right here, that 5 and that 15 cannot cancel. This plus sign, these two terms, neither one of them is available to be canceled. So what can we do? Step number 1, and this will be step number 1 in this entire chapter, factor. Let's look at this, factor the top, take out a greatest common factor. Now we have two numbers that are timesing together. If on the bottom we find an x that's a factor, we can cancel it. Or if we find a whole x plus 5, we can cancel it. What do we have here? 3 and a y can come out. And we have x plus 5. Alrighty, that is, look at that. And you slash them. These are the same principles that happened way back in fractions and now make what to do clear, even under very compelling and ugly circumstances. And we get x over 3y. Great. Let's try one more of those. X squared minus 36 over x squared minus 4x minus 12. Now, can those x squareds cancel? They cannot. We can't do anything until it is factored. So we need to factor it. The top is a difference of squares, so x minus 6, x plus 6, and on the bottom, this is a trinomial leading coefficient 1. So we have to think what times is to a negative 12, 1 and 12, 2 and 6, 3 and 4, that will add to a negative 4. So that's a positive 2 and a negative 6. That's x plus 2 and x minus 6. This whole x minus 6 is being times by something, so we can slash and burn that guy. And this reduces to x plus 6 over x plus 2. That is how we simplify fractions. We make sure they are in factored form, and then step 2, slash and burn. Excellent. Let's move on to multiply and divide. Let's first look at the principles we're going to be using as we did with fractions. If we had something such as 2/3 times 5/7, do you remember how we multiply fractions? Indeed, we just take 2 times 5 is 10 and 3 times 7 is 21. What if we had something like 2/3 times 3/5 times 5/7 times 7/11? What happened with this one? Well, on the top, you would take 2 times 3 times 5 times 7, get a number, and 3 times 5 times 7 times 11, get a number. Or you could leave it in factored form, since we're going to be factoring, and see what happens. 2 times 3 times 5 times 7 over 3 times 5 times 7 times 11. And notice that things cancel. And we're left with 2/11. 3 over 3, that's 1. 5 over 5, that's 1. 7 over 7. So you'll notice when multiplication happens, because we're timesing the tops all together and the bottoms, it's almost like you can extend this all the way through and put your little time signs in there, and then you can slash and burn by multiplying, like you did with simplifying. So let's see how something like that may work with rational expressions. If we had something like x over y times y squared minus 3y over 3x plus 5x squared. That looks ugly, doesn't it? All right, so first step, again, you're going to factor everything. Okay, so this is y times y minus 3, and this is x times 3 plus 5x. So we really have x over y times y, parentheses, y minus 3, over x times 3 plus 5x. So again, we just factored everything. Now this multiplication means that we're just connecting these dots and putting a times sign there and a times sign there. And slash. Again, this is where you're multiplying. You're going to just factor everything, and then you get a slash. Everything that's the same. Slash that, slash that, slash that, slash that. And we're left with y minus 3 over 3 plus 5x. And we're done. That's it. You have now simplified that ugly looking problem. So what do we do with divide? Well, let's try a problem, and I bet these basic fundamental principles will cause it to fall apart before our very eyes. Let's take a problem, x squared minus 49 over something like x squared plus 5x minus 14 divided by 3x squared plus 12x over x squared minus 2x. Looks like a horrendous looking problem, doesn't it? Indeed it does. So first step, let's factor. Well, but what do we need to worry about with divide? The one thing with division, if you remember how to divide fractions, is that this guy means multiply by the reciprocal. You may have heard it as keep it, change it, flip it, or flip and multiply. Gosh, if you're into the Napoleon Dynamite scene. So let's factor everything and see what comes up. So here we have difference of squares. So this becomes x minus 7, x plus 7. This guy becomes, this is a trinomial, trifast. So what multiplies to 14 and adds to a positive 5? Negative 14. That's x plus 7, x minus 2. Up here, greatest common factor, a 3x, and we get an x plus a 4. And on the bottom here is greatest common factor, an x, and pull out an x minus 2. Alrighty, so now when we write this, using all of these factored forms, we have an x minus 7 times an x plus 7 over this x plus 7 times x minus 2, and now it multiplies by this guy flipped on its head. That's x times x minus 2 over 3x, x plus 4. Oh, that's marvelous. Look at that. All right, so with multiplication, we're back to that one. So this one is just flip and multiply, and then we're back to multiplication, which we factored it, and now connect all the way across the top because multiplication just times the top and times the bottom. So slash anything that's the same on the top, anything that's same with anything on the bottom, anything else. There's an x there. Yeah, he's gone. He's gone. So we're left with x minus 7 over 3 times x plus 4. So you may leave it like this in factored form on the bottom, or go ahead and multiply that out and you get 3x plus a 12. Probably this way will be most common in the back of the book, but either one of them is correct. Okay, now you give it a try. To the boards! All right, here we are. Write these problems down, press pause, work them out, and then when you're ready to see the answers and see how you did and have had your practice, let's resume. Welcome back. Let's look at them. Here we're simplifying these, so they're already in factored form. They're all multiplied out. There aren't any plus signs in here, so we can go x's are gone and z's are gone. And so we're going to be, 18 and 24. In slow motion, that's 6 times 3 and 6 times 4, so the 6's can cancel, and we'll get 3y over 4r. There we go. Number 2. Factor the top. Can we take anything out of the top there? Yeah, that's 5x, and it leaves an x plus a 6. On the bottom, we have 2x squared minus 72, so we can take a 2 out, and we get x squared minus 36. This is in and of itself a difference of squares, so this should go to x plus 6, x minus 6. So let's write all that out. 5x, x plus 6 over 2 x plus 6, x minus 6. And look at what the same is. Shoom, shoom, that's gone. So we're left with 5x over 2x minus 6. And you could jump that through the parentheses and have 5x over 2x minus 12. All right, number 3. We should circle that. There's the answer right there. All right, on number 3, let me see. Factor everything. So this guy right here is x plus 3, x plus 5. That's a trinomial fast. This one, 2 times negative 21 is going to be negative 42, 1 and 42, 2 and 21, 3 and 14, 6 and 7. Add up to a negative 1, that's negative 7, positive 6. So this is going to take a little bit of time. It's a AC method, so it takes a little longer. 7x plus 6x minus 21. Chainsaw, so we get x, 2x minus 7. And over here, a 3. Yep, 2x minus 7. Good. And so that ends up being, let's put it over here. We're going to have the 7x. And then on this one, we're going to have the 2x minus 7 being taken out and being left with x plus 3. Let's write that down. All right, so that one's been factored. This guy's factored, the x plus 3 and the x plus 5. Good. And then the 6xm. All righty. This is multiplication, so we just extend that, and it's timesing up there and timesing down here, so everything's timesing and we're all good. X plus 3's cancel. The x cancels. Anything else? The 7, the 6? Nope. This 7 is not available for canceling. It is right next to a minus sign. It's only a portion of that factor. So we will be left with 7x plus 5 over 2x minus 7 timesing by 6m. Alrighty, there we go. And number 4, the last one. Let's change color so it gets a little bit, it's more distinguishable. This one's going to have a negative 28, and then this is a difference of squares. That's x plus 7, x minus 7. Okay, this one right here, 3 times 28. It's got to do an AC method. So 3 times 28 is 84. That's 1 and 84, 2 and 42, 3 and 28. We just did that guy. 4 and 21, 5 and, 6 and 14, and 7 and 12. I think is what we've got there. All right, we've got to add up to a negative 25. Notice that this one is tempting, but you'd have to have a negative 28 and a positive 3 to make a negative 25, and that's not a negative 84. We've got to look at a negative 21 and a negative 4. So let's do it down here. 3x squared. This came from a negative 4x minus 21x plus 28. Chainsaw, cut that in half, do grouping, and we have x, 3x minus 4, and over here pull out a negative 7, and we have a 3x minus 4. So that one factors into x minus 7 and 3x minus 4. Excellent. All right, let's write it all out over here, and we have the first one, which is negative 28 x plus 7 x minus 7 over 21xm squared. We are timesing it by, so that line will just extend, but let's reciprocal this guy, reciprocate it, 15m cubed. And then on the bottom we get this right here, x minus 7, 3x minus 4. Oh yeah, that looks ugly, but they're the two separate fractions, and the time sign means that that line can just extend straight through them. So the x minus 7s will go away. Let me see, the m cubed, we got m squared, so we'll take m cubed over m squared. That's subtraction of exponents, so that guy is completely gone, and that one will take it down to a power of 1. And then 28 over 21. A 7 can come out of there and leave a 4 and a 3. And the 3 and the 15, that'll leave a 5 and that'll leave a 1. Let's see what we have left. We have negative 4 times 5, so that's a negative 20. x plus 7 on the top. That's everything on the top times together. Oh, we have an m as well. Negative 20, we'll stick the m right there. Over on the bottom, we have an x, and we have the 3x minus 4. So there you go. Leaving it in factored form on the bottom and on the top means we could simplify, if anything simplified further, but that's about as far as we can go. Okay, let's look at the final topic. And finally, as one last thing, we are going to study how to graph the fundamentals of rational functions. So remember what a function is. You stick a number in, you get it out. And we did a bunch with lines, and then we saw some that were weird shapes. Well, now we're going to introduce you to graphs that aren't lines. So the easiest one to look at the very beginning is this one. This is take the easiest fraction, 1 over x, that has a polynomial right here. And notice this isn't in y equals mx plus b format. The x is on the bottom. So there are a couple of key points with graphing that you need to know. Number one, you never, ever divide by 0. Right? Never, ever, ever. That's horrible to divide by 0. It's undefined. So if we have a little x and y table here, let's write this thing out. Okay, so x and y. So when we start sticking numbers in, if you try sticking in 0 for x, you will get an error. We talked about that with slope. It's undefined. You can't do it at all. But you can stick in numbers that are like really, really small and close to 0. Like let's stick in 1/10. If we stick in a tenth, let's do this in a function notation. Do you guys remember that f of x? So let's do f of x equals 1 over x. So we can use that function notation that we learned a little while ago. F of 1/10 is going to be 1 over 1/10. Flip and multiply, and we get the number 10. Wow. Stick in a really small number, you get a big number. What if we stuck in like negative 1/10? Well, f of negative 1/10, that would be 1 over negative 1/10. Flip it upside down and we get a negative 10. Okay, so there are a couple of rules that happen that we start to realize with fractions that will help us to graph it because we don't have a common slope. We need to find more than 2 points, that sort of a thing. The first is never ever divide by 0. And if you remember what numbers can go in and what can't, that is where domain comes in. The domain of this function are all numbers that can go into it. Well, 0 can't. So the domain would be x doesn't equal 0. You write it like that. X can be anything else. So that's the first thing. The second thing is when you take the fraction of 1 over a very small number, it gets very big. Now notice that on the positive side, it gets very big positive, and on the negative side, it gets very big negative. So it gets huge, plus and minus big. That will come in handy when we're trying to draw it. Okay, what do you think happens when we do 1 over big numbers? Well, let's try it. If we were to stick in, let's say, 200, let's stick it in, f of 200, it would be 1 over 200, stick it in for the x. That's 0.005, I think, is what we get. Teeny little number. I'm going to put it in like this, 1 over 200. What about when we stick in negative 200? Very similar thing happens. Negative 200, and that 1 over negative 200. Which is going to be the same number, just negative 0.005. Yeah, 1 over negative 200, or negative 1/200th. 1 over big goes really, really small. Plus or minus, if this guy's positive, that guy's positive, if that guy's negative, that guy's negative. What happens is that these numbers, as you stick in like 1 over 200, and 1 over 1,000 is 1,000th, and 1 over a million is a millionth, these guys start going to 0. So it's some very interesting stuff that happens here on a graph. And so we are going to call this sketching a graph. So first of all, 0 is out of bounds. I'm going to put a dash down through here. Let's get a different color so you know it's bad. 0 cannot be put in, which means in this case, we do not have a y-intercept. That's normally our easiest problem to ever get, is a y-intercept, because you get to stick in 0. I'll put that right here, f of 0, because we'll come back to that. This particular one doesn't have it. You stick in 0, you get error, so we don't have it. But we do know a couple of points that are on the graph. When you're right next to 0 here, like 1/10, you're way up here. And when you're right across on the other line, you're way down here. Wow, and you can't cross that line or you would stick in 0. 0 is not part of the domain. So if we stick in smaller and smaller numbers, so get closer and closer to 0, we shoot up this way. You stick in smaller and smaller numbers, they get bigger and bigger. So as we stick in smaller and smaller x's, the y's that correspond to them are larger and larger. So there's an arrow here. This arrow right here, this is shooting and getting closer and closer and closer to 0, is what is called an asymptote. This is a line that a graph will get closer and closer and closer to, and helps us in sketching the graph. So if we know where these lines are, we know the arrows are going to go right next to it. One on one side and one on the other side. So it comes up here and does something. Let's see what it does. So this is what's called a vertical asymptote. And then what happens on the other end is what happens when we start sticking in really big numbers. You know what? We should stick in a good, nice, easy number every once in a while. Let's stick in like 1. If we stick in 1 for x, 1 over 1 is 1. We get 1 for y. So what about negative 1? 1 over negative 1 is negative 1. Oh, that's nice. We have some good points that we could also stick in. Let's highlight those. 1, 1, 1, 1. Negative 1, negative 1. So we go like this. Now what's interesting about these is that we already know what happens when we stick in huge big numbers, like way over here, like negative 200, and way up there at 200. It starts to get small. So this will get closer and closer to 0, and that will get closer and closer to 0. And I'm going to put this in here in a blue line like that. This is what's called a horizontal asymptote. And so these are the crucial elements. Instead of y equals mx plus b, the horizontal asymptote, the vertical asymptote, if we could find a y-intercept, that would be valuable. And the domain, those are the crucial things that help us to sketch the graph. We can also find some points like 1, 1 or negative 1, 1, but really where these arrows are heading kind of tell us where the graph is. So let's show you one more of those and how you can graph it. Let's look at y equals 1 over x minus 2. Yeah, 1 over x minus 2. So we're going to get first of all, the domain. Notice 0 is perfectly fine. Let's try that. The y-intercept, f of 0. If we stick in 0 for x, 1 over 0 minus 2 is negative 1/2. Notice we have a point, 0 and negative 1/2, right there. Okay, now let's try and find the vertical asymptotes. So the domain here, what number can I not stick in on the bottom? Well, I can't let x minus 2 equal 0. This is bad. If x minus 2 equals 0, I blow the whole function up. So x equals 2. So that's what's bad. So the domain is x cannot equal 2. That's the domain. So that means that x equals 2, let's get that red color out here. So over at x equals 2, we have this happening. We're going to have a vertical asymptote, and actually the official math term is that the function blows up at 2. If you're bigger than 2, then like 2.1, and you subtract these, you'll get a positive number. So we can tell that our graph goes up right here on that side. And if you're just below 2, like 1.9 minus 2 would be a negative 0.1. 1 over a negative 0.1 would be a negative large number. Yeah, and this will always happen. For a standard asymptote, not like you have 2 or 3 roots on the bottom, but if you have a standard asymptote, one side you're going to head up and the other side you're going to head down. That's what makes dividing by 0 so bad. Is think about it, if you could stick a 2 in, it's trying to be positive infinity and negative infinity at the same time. All right, this one's nice because we know it comes up here and has to hit that one point. And then what happens if you stick in like horizontal asymptote? Let's stick in a billion. Let's label this guy horizontal. Because if we stick in like really big numbers, we know where we can draw that arrow to. So 1 over a billion minus 2, or, oh, we're headed out the negative direction. If you stick in negative a billion, 1 over negative a billion, we're going to get a tiny little number and it's going to go to 0. So it's heading to 0. So our horizontal asymptote would be y equals 0. We're going to get closer and closer to that. You'll notice the same thing happens if we stick in really big numbers here. We get closer and closer up there. So we have y-intercept, horizontal asymptote, and vertical asymptotes. Excellent. Now we'll give you a chance to do some on your own. To the boards! And to the board you go. Here are 2 problems that you are asked to sketch the graph of 2 functions. Look at this notation we're using now. 2 of these and sketch the graph. Label the domain. You'll find it valuable to find any y-intercepts and vertical and horizontal asymptotes. Pause the video now, write these down, work on them, and then unpause and let's see how you're able to do. All right, welcome back. The first thing that's most crucial to do is to find out what numbers cannot go in there. And we cannot make the bottom 0. And you'll be able to see that if x minus 2 were 0, x would have to be 2. So the domain is all x's that do not equal 2. And back in chapter 2, we had some fancy way of writing that with some garnish around there. But right there, x cannot equal 2. That's the most crucial thing. So let's find some of the other easy ways, easy points and things that will help us graph it. So x-intercept. Okay, the x-intercept is, if we stick in 0, so we stick in 0 for x. This is also known as f of 0. So we stick in 0 for x and we get 6 over 0 minus 2. That becomes 6 over negative 2 is a negative 3. So 0, negative 3 is a point. Of all the things we do, that's a real point on the graph right there. We also note that our domain, what we can't do is our vertical asymptote. Vertical asymptote, x equals 2. This is not part of the graph. This is the part that we can't touch. So I'm going to put a dashed line right here, and it means we're going to shoot up on one side of it and down on the other. And you can see this guy's already headed down, so we're going to keep drawing that. And that guy goes up like that. And the horizontal asymptote. What happens when we stick in really, really big numbers and really big negative numbers? What happens? So if we stick in a billion here, we get 6 over a billion. Yeah, anything over really big numbers goes to really small, so we're going to get a horizontal asymptote. I'm going to extend it out here, that as we go out this way, we're going to get closer and closer to 0. And look at that. With that information, we were able to say kind of what this graph looks like. That's kind of fascinating. All right, let's do the other one. So over here, the domain, first thing, is what is the worst number in the world for this particular function? And it is that x cannot equal negative 8. If you stick a negative 8 in there, negative 8 plus 8 will give you a 0 on the bottom, and we must never, ever divide by 0. So there we go. All righty. Okay, good. So the domain is that x cannot equal 8. Any other number you can stick in. So let's get the y-intercept. Oh, we should label the vertical asymptote while we're here. Vertical asymptote is where x is 8. So it's clear out here. Oh, I just did x equals 8. It's x equals negative 8. So we know that line. That's the bad line, and so we're going to get an asymptote where we shoot up and down on that guy. Let's see where our y-intercept is. If we stick in 0, we get f of 0 is 2 over 0 plus 8, which is 2 over 8, which is 1/4. So positive 1/4. So you can kind of tell that this guy is going to be heading out to 0 that way, just like it has in the past, and is going to be heading up that way. So the vertical asymptote, let's mark that, 1/4. Vertical asymptote is x equals a -8. And is there a connection between that vertical asymptote and the domain? Of course there is. That's the one we can't do. And so over here, it shoots up one side, it shoots down the other. And what happens if we stick in negative billion, billion, billion? We're going to get close to 0. And that's really all it is you say, where do the arrows go when they're headed out these directions and they're heading to 0? Where's the bad number that we shoot up and down? And let's get 1 point just to peg things down. And that is how we sketch the graph of rational functions. And yes, indeed, this actually is what it looks like. Good, you'll be able to do your homework.